Now we go to the definition of circular motion. So they said that if an object moves along a circular path at a steady speed means uniform, and circular path is nothing but circular. So the answer should be A, right? There is nothing to be thought of. It's easy. Circular path, steady speed, so uniform circular motion. The next question is about vectors. So they said that at the position shown in the diagram, which arrow indicates the direction of the tangential velocity? Tangential velocity means tangent. The only tangent vector here to the circular path is c. So that's v. That's the velocity v. So it's a tangential velocity. It's v. Then, at the position shown in the diagram, which arrow indicates the direction of the centripetal acceleration? Centripetal acceleration means towards the center. Towards the center, the only vector which is pointing towards the center is A. So that's the centripetal acceleration, A. Then, we just mentioned here that centripetal acceleration is directed towards the center. And here they're asking us in number 18 about centripetal acceleration always points to the something of the circle. That something is the center of the circle. Next, so they gave us here a carnival ride has a 3 meter radius, so that's the radius, and they told us that it rotates once every 1.7 second. This is the period of revolution, t. They're asking about the speed. Speed is nothing but 2 pi r over t, which is 2 times 3.14 times 3, 2 pi r over t, which is 1.7. Now, when you put this on the calculator, it's going to give you 11.08 meters per second. The closest answer is D. Then, what is the centripetal acceleration of the rider? Centripetal acceleration has a formula AC equals to V squared over R. V, we found it to be 11.08 squared over the R is 3. This answer is nothing but 41 meters per second squared. But you're going to tell me, Mister, we have A and B, both of them are 41 meters per second squared. We have to know that when we have a circular motion and the object is somewhere, let's say here, okay, of mass m, and this is the center of the circle, the centripetal acceleration is directed towards the center of that circle, which means that this is inwards, not outwards. So it's inwards. B. 21. In circular motion, centripetal force is always directed towards. Again, the centripetal force is the same as the centripetal acceleration. They have the same direction, both, because already the centripetal acceleration is caused by a centripetal force. So they have the same exact directions, both towards the center of the circle. It's B. Then suppose you whirl a yo-yo about your head. So let's say this is your hand. Here you have a yo-yo and you are whirling it. And you are whirling it in this direction like this. All right. So when you are whirling it in this direction, actually, there is a string, right? So in what direction must the force act on the yo-yo? It has to act, I'm going to use this color. It has to act in this direction, the force. And it's actually a tension force, which is equal to a centripetal force. Okay, so this is the case when it comes to the force. So in what direction must the force act on the yo-yo? Uh, so towards the center of the circular path. In this case, it's towards your hand, by the way. So towards the hand, in this case. All right. What exerts the force? It's a tension in the string. So tension, force in the string. Next, an athlete whirls a 7 kg hammer 1.8 meters from the axis of rotation in a horizontal circle as shown in the figure below. The hammer has an acceleration 71 meters per second squared. So 71 meters per second squared is the centripetal acceleration. 7 kg is the mass, and 1.8 meters is the radius. What is the tension in the chain? They want the tension, which is this one. They want the tension force. So the tension force is a centripetal force. It is equal to the mass multiplied by the centripetal acceleration, which means 7 multiplied by 71. 7 times 7 is 49, so 490, 497. It's almost 497 newtons. Now we can take it approximately to be 500 newtons, and in your answer key, I believe it's written 5 times 10 to the power of 2 newtons. It's okay, all of them are accepted answers. Now, again, another athlete, this time has a 10 kg hammer, so that's the mass. Uh, 1.8 meters is the radius, and they said that the hammer has a constant centripetal acceleration. AC is equal to constant. Okay, and it's 80 meters per second squared. They said determine the tension in the chain. So again, tension is a centripetal force in this case. It is equal to mass times centripetal acceleration. The mass is 10. The centripetal acceleration is 80. 10 times 80 is equal to 800 newtons. On the figure above, mark with an arrow the direction of the centripetal acceleration. It's already marked, but I want to show you here from another perspective. Let's say it's not here, but it's here. Let's say the hammer is here, and this is the center of the circular path. The acceleration is going to be pointing towards that center. Okay, that's it. Now, another question. They said for each situation below, what provides the force that causes centripetal acceleration? You may want to draw a diagram. Okay, so they want us to tell them in each case which force is causing the centripetal acceleration. A ball on a string swinging in a circle in uniform circular motion. So you have a string. At the end of the string, you have a ball, and that ball is swinging in a circular path. So in this case, the centripetal force is caused by the tension in the string. So tension in the string. Satellite moving around Earth in uniform circular motion. The gravitational force between the satellite and the Earth is the one causing this centripetal acceleration. So we can write here uh, gravitational force between satellite and Earth. Uh, we wrote it the wrong place. It's all right. So gravitational force between satellite and Earth. Car driving in a circle in uniform circular motion. That's the friction between the tires and the road. So friction between tires and road. Person in a carnival ride that has, excuse me, that has hanging baskets that are whirled around horizontally in uniform circular motion. It's the case that you have a chain, and you have actually two chains, and the basket is tied to those chains. All right, and the carnival ride is basically turning around. So this basket is acted upon by a centripetal force, which is a component of the tension in the chain. So a component of the tension force in the chain. Now, let's go to 7.1. Explain Kepler's first law. So, according to Kepler's laws, the paths of the planets are they are actually ellipses, and if this is one of the planets, okay, revolving, orbiting around the sun is at one of the focuses of this ellipse. So that's the sun actually. So it's an ellipse, and according to Kepler's first law, the sun is located at one of the focuses of the planet's orbit. This is done. Then this is actually Kepler's second law. According to Kepler's laws, of the following, which of the following statements is true? All planets on the path of the planets, all points on the path of the planets orbit are equidistant from the sun. Actually, they are not, because I already drew it here for you. For example, if the planet is here, its distance is far from here. So look at this. This distance is closer than this distance. All right, so next, A is wrong. Planets move faster when they are closer, that's correct. And slower when they are farther away from the sun. So closer to the sun, faster. Away from the sun, slower. So answer is B. No need even to continue the rest, because they are already wrong. Kepler's second law states that a line joining a planet and the sun sweeps out equal areas during equal intervals of time. That's the answer. It's equal intervals of time. Uh, so That's also second. 28 and 29 both are Kepler's second law. Now, Kepler's third law. In Kepler's third law, we can see clearly here that the period of revolution of a planet around the sun is proportional. I mean, the square of that period is proportional to the cube uh, of the radius. So if the radius of the planet's orbit were doubled, multiplied by two, what effect would it have on its period? The If you are increasing the radius of the orbit, uh, then the period also will increase because, I mean, the square of the period is proportional to the cube of the radius of the orbit. So actually, that's the case. Uh, 1 second. So yeah, done. It would increase. The attractive force that exists between all masses, if you have a mass here, M1, and if you have another mass here, which is a little bit bigger, okay, M2, and they are separated by, their centers are separated by a distance r, okay, there is a force between them. It's a force of attraction, actually. So this force of attraction is like this. They attract each other, okay? So those two forces are equal in magnitude, opposite in direction. It's a gravitational force. It's a gravitational force. Then, according to the formula, Fg equals to G m1 m2 over r squared. If the mass is doubled, if one of the masses is doubled, here they said the sun's mass is doubled, what's going to happen to the attraction force? Um, Take it this way, actually. So Fg nu, okay, equals G m1, and you're doubling m2 over r squared. You can take this r because it's a multiplication. So when you have a multiplication, when you have a product, just take it out. So the 2 is going to be out. 2 G m1 m2 over r squared. This is nothing but this one. So it means that the new Fg equals to 2Fg. So it got doubled. So if you double the mass of the sun, the gravitational force doubles. Now, regarding this question here, which is about uh, which object pulls on you with the greatest gravitational force. So um, your mass is remaining the same. Okay, so Fg equals G m1 m2 over r squared. The only two things which are changing are m2 and r. Uh, okay, so here, look, m is changing and the distance is changing, but they said pulls on you. So your mass actually is not changing. So m1, I'm not changing it. G is already a constant. G is always 6.67 times 10 negative 11. Okay, so in order to do so, I need to find the ratio m2 to r squared every single time. So 1.2 over 15, excuse me, 0.2 squared, and then 15 over 1 squared, and then 20 over 2 squared, and then 70 over 10 squared. Now, if you do on the calculator 1.2 divided by 0.2 squared, it will give you 30. So 0.2 squared is 0.04. 120 divided by 4 is 30. Yes. 15 over 1 squared is 15. 20 over 2 squared is 5. And 70 over 10 squared is 0.7. And they were asking about the greatest gravitational force. It's already obvious which one is the greatest gravitational force. It's this one. So the answer is A. Now, number 34. They said Mars's mass is 1/9 of Earth mass. So the mass of Mars equals 1 out of 9 the mass of the Earth. And they said that we have two satellites, one orbiting Mars and the other one orbiting Earth. Do we need the masses of those um, satellites? No, we don't need. But we need to know that both of them have the same orbital radius. Yes. So the one orbiting the planet Mars is at the same distance from Mars as the one orbiting Earth. So those two are equal to each other. Now they're asking which one has smaller period. So, first of all, I want to tell you that the period of revolution of the satellite orbiting Earth is nothing but 2 pi square root of RE squared, or I'm gonna just take it as, okay, I'll leave it RE squared over GME. Then I'll take the period of revolution of the satellite around orbiting around Mars. So it's 2 pi square root. The orbital radius is remaining the same. So I will take it as RE squared over G. Now, the mass of Mars is 9 times smaller than the mass of Earth. So I would take it as 1/9 of ME. Now, according to the rule of math, in mathematics, you have a rule, keep, change, flip. The 1 over 9, which is at the denominator, can come up when you take this and you put it up, it will flip. So it will become, instead of 1 out of 9, it will become 9. So TE, excuse me, TM equals 2 pi square root of, instead of 1 out of 9, which is at the bottom, take it up, it becomes 9 RE squared over GME. Now this 9, it's under the square root. You can take it out. If you take it out, you have to take its square root. Square root of 9 is nothing but 3. So Tm would be equal to 3, 2 pi square root of Re squared over GME. Now this, all this, is nothing but the period of revolution of the satellite around Earth. So Tm equals 3 TE. So the which one is smaller, TM or TE? TM is bigger than TE by 3 times, is larger than TE by 3 times. So it means that TE is smaller than TM. Okay. That's also done. According to the given formula, t equals to 2 pi square root of r cubed over gms, what happens to the orbital period t of a planet if the radius of its orbit r increases? I can see here from the formula that t equals to 2 pi square root of r cubed over gm. I can clearly see that t is proportional to the square root of r cubed. So if they said r increases, then t would also increase, right? That's the answer. Next, the speed of a satellite orbiting Earth is proportional to. Okay, let's write the formula first of all. V equals square root of GME over R. Okay, I can clearly see that V is proportional to the square root of ME. Okay, so the answer is this one. But please be careful because on the answer key that you have, um, the wrong answer is circled, the wrong option. They, I think, circled A, which is wrong. It has to be B. Okay, then two satellites orbit the Earth. As shown in the diagram. The orbital radius of the satellite S2 is twice, so let's write down here that R2 equals to 2R1. And if you want to know about V1, V1 is square root of GM over R. Um, R1 in this case, actually. Okay, which is equal to V. They said take it as V. They want you to find V2 in terms of V. Okay, V2 equals square root of G M. Actually, the satellite's mass is not changing. It's the same. Both are identical satellites. So GM over, the only thing which changes is R. So R2 is 2R1. So you can write 2R1. Now I can see here that 2 is at the denominator. So if you take it out, you should take it out as 1 over square root of 2. And then if you want to keep something inside, I actually want to move. So equals 1 over square root of 2 and square root of gm over r1. This square root of gm over r1 is nothing but, this one here is nothing but v. So v2 equals 1 over square root 2 v. And you can multiply them by each other. So v times 1 over radical 2 is this answer. So it's B. Then they told us here that an object is weighing 250 newtons on Earth. If you take it away from Earth by exactly the same distance as the radius of Earth, which means that you are doubling the distance. So instead of being RE, you're taking 2RE. Okay, what's going to happen to the weight of the object? The weight of the object, definitely, it's going to decrease. So as you move further away uh, from the Earth's surface, the gravitational acceleration becomes smaller, which means that the weight also becomes smaller. So it is 250. Now, smaller means that it's either A or B. But we have to do the calculation because without the calculation, I'm not going to be able to find out. So let me first find the gravity at that distance. How much is the acceleration due to gravity. So G equals GME over R squared. But the new G in this case is going to be GME. G is not changing, the mass of the Earth is not changing, only the distance is 2RE squared. Okay, so 2 squared is 4, so this means that it becomes GME over 4RE squared. Now equals to 1/4 of, what's this? This is nothing but G. So 1/4 of 1/4 of G. It means that if acceleration due to gravity decreased 4 times, okay, it means that the weight also decreased 4 times. So the weight, the new weight, equals to the old weight divided by 4. So 250 divided by 4. 250 divided by 4 is approximately 63. Next. A gravitational field surrounds anything that has mass. So any mass like this is surrounded by gravitational field, which is directed towards the center of that mass. So the region around Earth is in which objects experience a force due to Earth's gravity is called gravitational field. In which direction does the force of Earth's gravitational field always act? Towards the center of the Earth. So they're asking about in which direction does the force of Earth's gravitational field always act? It's towards the center. I drew it even here. This is the center of Earth, let's say. Okay, so yeah, this is it. Now, number uh, 42. They gave you 200 kilometers away from the surface of Earth. So please, this one, you should change it to 200 times 10 to the power of 3 meters. First, we change it to meters. They want the gravitational field strength. The gravitational field strength, the formula is Gm, طبعا it's mass of Earth, over Re. Now we would take it Re squared if the object is on the surface of the Earth. But the object is, imagine, this is the surface of the Earth, it's somewhere here, which is 200 kilometers away. So I have to take into consideration not only the radius of the Earth, but also I have to take into consideration that it is 200 kilometers away. So I have to add h squared equals G is 6.67 times 10 to the power of negative 11 times the mass of the Earth is 5.98 times 10 to the power of 24 kilograms. Now you're going to ask me, how did you know this? It's going to be given in your formula sheet. All right. So that's that. Over. Now the distance, the radius of Earth is, let me quickly check. So the radius of Earth is 6.38 times 10 to the power of 6 meters. Okay, plus we have the 200 kilometers, which is 200 times 10 to the power of 3. squared. If you put all of this in the calculator, it's gonna give you that the gravitational field strength 200 kilometers away from the surface of Earth is about 9.21 meters per second squared. Okay, then number 43. A newly discovered planet has the same radius as that of the Earth and 8 times the mass of the Earth. How much is the gravitational field strength on the surface of that planet? So, first of all, gravitational field strength on Earth is GME over RE squared. And then the new planet, GP, equals G, but it has 8 times the mass of Earth. It's 8 times more massive. So I would take as 8 ME over the radius is the same, they said. It's not changing. Now you should take this 8 and put it here outside. So it would become 8 GME over RE squared. And this GME over RE squared is nothing but GE. So equals to 8 GE. So that's the answer here. Very good. Finally, if the distance from the center of a planet to an object doubles, how does the gravitational field strength experienced by the object change? So they're actually telling you that uh, the radius is changing, or let's say not the radius, but uh, the distance from the center of the planet. Okay, you take just again, GE is nothing but GME over RE squared. And they said that R is doubled, right? So new G equals GME over double the distance squared. Now, if you notice, I'm putting this bracket. It means that the 2 is as well squared. So if you do it that way, 2 squared is 4, RE squared is just RE squared, and GME at the top. Now, again, I said here, look at this. This is nothing but GE. So G new equals GE over 4. So it is reduced to 1/4. And that's the answer. Now the questions are done. I'm going to wish you uh, a good luck and uh, study well. And if you made it until here, this is amazing. All right, so I'm going to stop presenting and then stop recording.